So we're talking about scattering amplitudes. Scattering amplitudes. So we discussed last time that to introduce, so scattering means you have interactions, right? To start with. So you have to pass from the discussion of the free string to the discussion of the interacting string, right? And interacting string means you replace your free string worldsheet, which is a cylinder in the case of closed string, by some homogeneous Riemann surface, not necessarily homogeneous, but at least a Riemann surface with several cylindrical ends, as we discussed. But it could as well be, so this, for example, this corresponds to a 4-point scattering function, scattering amplitude. So the idea is that there are these infinite cylinders, right? I draw them as kind of truncated legs, but they are infinite cylinders. So this is meant to represent a free string that kind of starts propagating as a free string, then they kind of join, interact, and as well it could be of higher genus. That corresponds to loop corrections in quantum field theory. And we discussed that to get, so we want to approach this in some more intuitive way. So how do you get this kind of geometry? So first of all, your metric, your worldsheet metric, which is e to the phi dz bar. It has some singularities as you approach these infinite cylindrical ends. Well, actually, although it looks like infinite cylinders, you could as well equivalently think of it as a sphere, or maybe, okay, this is not a sphere, this is a torus with some marked points, right? It could be, you take the surface of your genus and you assume there are some marked points, and near every marked point, the metric behaves as, so has a cylindrical type behavior, so dz bar. So you can either think of it as a surface with marked points, or you imagine it as this kind of surface with infinite legs. When you think of it as a surface with marked points, you should take into account that the distance to these points is actually infinite. So actually, if you think of it as embedded in some kind of Euclidean space, then this is translated into those infinite legs. Then you may think what kind of solutions in the sigma model, in the string sigma model, will give you this kind of behavior. So if you think about the this ds squared as ds squared induced, so is dx mu d bar x mu dz bar, and we found that the x should have some logarithmic singularities at as z goes to z bar, and therefore there are some sources. Secretly, there are some sources that sit at those points. And from the point of view of the your theory, that this looks like we're calculating some correlation functions of several operators. So we are calculating some correlation function. Which can be presented as a path integral, right? It's equal to some path integral. But the point is that these operators are exponential operators, so v k of z bar is e to the more usually written as the form of normal ordered exponent. So you need normal ordering to cancel some naive divergences that will arise if you don't have normal ordering, right? So normal ordering just means that in your correlator, you prohibit contractions of the fields inside sitting in inside one operator with themselves, right? So if you expand this as in a Taylor series, you cannot contract two of the x's coming from the same operator. You can only contract the x's from different operators. That's always what normal ordering means. Okay, and this is called the so-called vertex operator or tachyon vertex operator. So the most important point is that this is a scalar field vertex operator. Yes, so scalar. So the scalar particle being the tachyon in this case. So it's called the tachyon vertex operator. Analogously, you can build vertex operators for other particles in your spectrum, but to fully understand it, you would have to use what is called the operator state correspondence in conformal field theory. All right, so there is some what is called operator. So that means that on the one hand we had our states, so states which were characterized by the fact that, remember, L0 minus 1 times your state psi and LK psi greater than 0, and modulo some states that have 0 norm. So there's also some equivalence relation. So modulo 0 norm states. So you can pick such physical states satisfying these conditions, and you can map it to some operator. So some operator which quite generally has a form of some polynomial in dx, d2x, etc., various derivatives of x, acting on e to the I k mu x mu of z bar. And in principle, that's all should be normal ordered. So this is some polynomial in this polynomial. So particular examples are precisely the tachyon. So if p is p equals 1, so this is a tachyon vertex. Then say p equals xi mu dx mu. This would be vector field vertex in the open case. So this is an open. So yeah, in the closed case, you also have anti-holomorphic derivatives here as well. And so on. So there are more complicated operators. Like a simple example of how this works is you take the scalar field x, whose whose expansion we've written out earlier. So it's x mu plus and then you calculate the operator dx. So dx is yeah, so minus I. Actually, you can just write it as minus I. Or all n's, and so that you just differentiate this, and then you see that you consider the state 0, 0. So this is a state annihilated by all. So this is what is called an SL2 vacuum. So this is a state that annihilated by all oscillators with positive indices. And also of zero momentum. So that means P mu 0, 0, which is the same as what we call alpha 0, is 0. So if you consider this state, so for example, you find that limit of z to 0 of this dx mu acting on this state gives you minus I over square root of 4 pi t alpha minus 1. So you take your operator written in these z variables where the origin is the infinity of the cylinder, right? And you send, just act with the state on the vacuum vector, and so let z goes to 0. So here the singular guys will annihilate the vacuum, the regular guys will disappear, and only a single term will remain that gives you some state. And analogously, you can deal with other states. So, well, roughly speaking, the second derivative of x will give you alpha minus 2, and so on and so forth. So derivatives are in one-to-one correspondence with the indices of the oscillators. Of course, I mean, at higher level, you have to be a bit careful, but in the definitions. But roughly, that's the idea. And so in this whole picture, this tachyon vertex operator, the exponential operator, plays a distinguished role, right? Because the point is that this guy, so which state does it generate? Well, it generates a state of momentum k. Okay, so that's the role of this exponent. Just because by the same logic, all oscillators here will cancel out, and you will just be left with the usual quantum mechanical exponent ikx, which is a state of some momentum, right? When you generates a state of some momentum. So that's the kind of the general structure of this guy. So this exponent gives you a state of some momentum, and these polynomials in the x's, the derivatives of the x's, they give you the oscillators kind of acting on the state. But actually, we are only going to calculate scattering of this scalar field, the tachyon field, because as you imagine, once you start computing correlators of these guys, of some polynomials of x. This will be like a whole big additional structure, because as you see, they will have some parameters. For example, the polarizations, right, of your particles, like what I've written there, that the vector field is something like xi mu dx mu. So this xi is a polarization vector, right? Because the vector field has polarizations. So for each polarization, you have some state, and you have some operator. So in general, your amplitudes will depend on those polarization vectors. And as you probably know, in say amplitudes in gravity, they're extremely complicated. I mean, even tree-level amplitudes. So because of the index structure. And these are roughly, I mean, amplitudes in gravity in the simplest for graviton scattering, right? For higher massive, higher spin particles, they will have even more indices, and so on. So, anyway, so the point under this map between states and operators, well, what do we have? So we have these conditions. And what does it mean from the point of view of conformal field theory? Well, this means that you have a conformal primary state of weight 1, right? Of conformal dimension 1. In conformal field theory, you typically want to find primary operators. And they're characterized precisely by these properties, and the dimension of the operator is what stands here, right? So there is some delta, but here delta is 1. So, so under this map, this maps to operators. So primary operators V of z bar. I mean, this is general V, not necessarily the tachyon vertex, any vertex operator. So of dimension 1, 1. By 1, 1, I mean that there is a holomorphic part and the anti-holomorphic part in the closed string case. Alternatively, what does that mean? That means that you have a energy momentum tensor, right? T of z, which is in our case is just dx mu squared. And the OPE of the energy momentum tensor with your vertex operator has the prescribed form, right? So T of z times V of WW bar is the dimension by z minus W squared times V of the bar plus 1 over z minus W dV plus regular terms. So, so actually, to describe the spectrum, there is this alternative way. You can, instead of constructing states, the way we did before, using oscillators, right? You could just consider a general polynomial of some prescribed degree, let's say, or with some exponential operator like this, and then you require that its OPE with this energy momentum tensor of this simple form has this form with delta equal to 1, right? And this way you will recover the operators dual to those states. So there is the statement is an equivalent way of describing the spectrum. So instead of doing kind of quantization on a cylinder, where you expand in Fourier modes, blah, 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 then you act with these oscillators on your Fock space vacuum, right? And you impose Virasoro constraints on those states. You could just work with local operators using this OPE with delta equal to 1. And you will recover the spectrum. So that's the point. And I remind you that this delta equal to 1, that was precisely our A, right, also. So delta is A. is 1. So that is this normal ordering ambiguity that we encountered as a normal ordering ambiguity. And then we saw that by, say, Lorentz invariance or absence of the conformal anomaly, this has to take this value. So I mean, Lorentz invariance in a light cone gauge or absence of Weil anomaly in conformal gauge, it has to have this value. And what is special about this dimension 1? So if you have an operator of dimension 1, 1 on a Riemann surface, it means it's a form of type 1, 1. So actually, when you have this operator, it's kind of very natural to integrate it over your Riemann surface. You're integrating a form of rank 2, if you like, of type 1, 1, like dz bar form over your Riemann surface. And that's going to be a conformal invariant because V transforms exactly contragradients to the transformation of the measure. So this is weight 0, in other words. So this is a conformal invariant. So this means weight 0, 0, 0. And as we will see, we actually need such integrated operators to compute the amplitudes. Okay, so I mean, last time we noticed that these Riemann surfaces with long ends, they are naturally related to correlation functions of n such vertex operators, such tachyon vertex operators. Now let's compute this correlation function, right? So we want to compute the this correlation function vk1 c1 z1 bar. This is given by a path integral e to the by alpha prime integral d to z dx mu d bar x mu plus I sum over this k mu j x mu or zj bar. That's exactly what we discussed last time, that the equation of motion of this kind of theory will give you the surface whose induced metric is the metric with those infinite cylinders going to infinity. So let's actually compute this integral. So this is a Gaussian integral, right? So this is Gaussian integral. So how do we compute a Gaussian integral? Stationary phase, yes. So that's right. But it's kind of exact stationary phase here, right? I mean, stationary phase is a general notion for any integral in some particular limit, right? But here it's exact. So the exact value of the Gaussian integral, you just compute the stationary value of the exponent, which means solving the equations of motion, and then substitute the solution back into the exponent, right? I hope you're familiar from quantum field theory course, but that's just a general property of Gaussian integral, right? So here the equation of motion is, we've written it out earlier, was d bar x mu minus I over 2 t sum mu. So this is the equation of motion. So we're just varying the exponent with respect to x, right? This is the Poisson equation that we started with, but now let's write down the solution of this equation. So the solution is prime over 2 sum p mu j log z minus zj squared j from 1 to n. Right? So, I mean, formally we're just solving a Coulomb problem, right? We want to find the potential of a system of charges located at points zi. Right? Our density is delta function like. The delta functions are the positions of the charges, so we want to know the potential. The potential, well, you have to know the Green's function of your Laplace operator, right? So in 3 dimensions, that would be 1 over r, the usual Coulomb potential. Here it's logarithmic, like, because it's 2 dimensions. So that's the general solution. Yeah, alpha prime is, so t was 1 over 2 pi alpha prime. This was a relation between the tension and the slope. So alpha prime is just for convenience. Now let's assume that x mu is regular at infinity. Z goes to infinity. So if you remember, actually we're working on a sphere, right, with marked points. So this is z1, z2, etc., zn. Sphere with marked points. So from this perspective, infinity is not a special point. These points don't have to be at infinity. So it's natural to assume that x mu is regular at infinity. But that means that the sum of the momenta is 0, right? Because that's the coefficient in front of log z squared, log modulus z squared, right? So if it's not 0, then it has a logarithmic singularity at infinity. So what it means is that if it's not 0, that means that actually you secretly have another operator at infinity, or another charge at infinity. So you haven't written it out explicitly, but it's there somehow. So then you have to add that charge to your collection of charges, and the sum of that means that the sum of charges is 0, right? Basically. So if in a sphere you have the sum of charges that is not 0, that means you have actually another charge at infinity that counterbalances these charges. But we can just assume that all the operators or all the charges are at finite points. So at infinity everything is smooth. Then you just have momentum conservation in this language, right? So this is momentum conservation. So that means that actually your correlation function is proportional to the delta function of sum of momenta, which is actually good, right? Because we expect any scattering amplitude in field theory is proportional to a delta function of the sum of momenta. I mean, in a translational invariant field theory. Right? I hope you remember from quantum field theory, if you compute some scattering amplitude, there's conservation of momenta, means that it's formally proportional to the delta function of the sum of all momenta. So here, the correlation function of these vertex operators is also proportional to the delta function of sum of momenta. So, and then what you need to do is you need to substitute this solution back in the exponent. Okay, so substitute back. Substitute back in the exponent. I mean, that's the usual way how you compute Gaussian integrals. That's effectively the same as completing the square in the exponent, right? You have a quadratic term, a linear term, you complete the square, then you shift the variable. That's the same thing, but usually in kind of physics language, we don't like to complete the square because your quadratic form is some differential operator, right? That's why we say we solve equations of motion, but it's the same thing. So the correlation function, once you substitute everything, will have the following form. So VK1 is the exponent of alpha prime over 4, sum of I not equal to j, EI of KI, KJ, log DI minus DJ squared times the delta function of the sum of momenta and in other words, this guy here is the product I smaller than j right. Well, alpha prime, you need alpha prime here to have this is dimensionless. So the exponent is dimensionless, right? Each momentum has dimension of mass. This has dimension of 1 over mass squared. And this, the brackets mean scalar product in Minkowski space, right? I hope it's clear. I mean, so K with P is eta mu nu, K mu P nu. So you see, once you substitute this, you get something like K times P, and by the way, should be K here also. So K everywhere. So you get this kind of correlation function. There is this delta function of momentum conservation, and these are called Koba-Nielsen factors. I mean, this is a useful calculation in general. In a theory of free bosons, you always have this kind of correlation functions. Yeah, so this is actually unrelated to string theory. You just have a two-dimensional free boson. There's a notion of vertex operator, which is an exponential operator in that free field. And you want to compute its correlation function, it will always be of this form, right? These kind of factors. Okay, and yeah, so for example, I mentioned that these guys are tachyon vertex operators. This means that they are of conformal dimension 1, 1. So delta, delta bar. Well, how do we see that? How do we see that? So what does it mean? So that means, as usual in conformal field theory, right? The conformal dimension governs the two-point function of the operators, right? So we should be able to see that from the two-point function. So let's compute the two-point function, Vk of z1, z1 bar. P of Z2, Z2 bar. I won't say that these momenta here standing in these operators are actually not arbitrary. That's what brings us to the string theoretic setting as opposed to generic setting. So in a generic conformal field theory, you can just take arbitrary exponents of your scalar fields. These are perfectly fine vertex operators for any k. Their correlators will be given by this expression. That's it. But here k are constrained by the requirement that they are of this particular conformal weight. So, so this is something like delta k plus p. Should be of the form z1 by general conformal invariance. So this is z1 minus z2 to the power 2 delta, z1 bar minus z2 to delta bar, which in this case means this should be delta function of k plus p divided by z1 minus z2 to the power 4 delta. And so in particular, if delta is 1, then this is just, so these operators have dimension 1, 1, 1, if this is z1 minus z2 to the 4th power. So what does it tell us about the momenta? Well, from this formula, we can derive, right, as a simplest case, when n is 2, we find that the correlator of Vk of z1, z1 bar, Vp to z2 bar is delta function of k plus p, delta function of k plus p, times modulus z1 minus z2 to the power alpha prime k with p. And since p is minus k, so this is minus, so this is delta function of k plus p, z1 minus z2 to the minus alpha prime k squared. Right. And now you compare that answer with this answer here. To find that alpha prime k squared is 4. And that's the mass shell relation of the tachyon operator. Right? K squared is m squared. Minus m squared. So this is m squared is minus 4 over alpha prime. This is a closed string tachyon. Closed string tachyon. So, so the requirement of prescribed conformal dimensions tells you that these momenta are constrained. And that's the kind of mass shell condition. Well, the claim is that same will hold for higher vertex operators. So if you derive vertex operators with given conformal dimension, well, so if you use the OPE with the energy momentum tensor, setting delta equal to 1, they will automatically have the right conformal dimension, right? Then if you compute their 2-point function, they will automatically have the. Alternatively, like I mentioned to you that T of z is dx squared, and if we consider our vertex operator as e to the ikx, and you start computing the OPE of these two guys, right? So you expand, for example, you can expand this guy in Taylor series and contract the two x's from here. So this is kind of dx squared times some 1 over m. So you have to contract 2 of the x's here with 2 of the x's there. Okay? And in this way, you precisely will get k squared. So this will be proportional to k squared over z squared times something that will remain, which will then resum back into your vertex operator. So you will get k squared over z squared times your vertex operator. I mean z minus w squared, right? So that's another way to see. And since you want this to be 1, roughly speaking, then you get again this condition. Well, there is alpha prime somewhere, which I have forgotten. So I mean, there are different ways. You can either compute the OPE, or you can compute the 2-point function. The result is the same. Okay, so let's do our last calculations. So far, we've computed this correlation function of the unintegrated vertex operators. Well, we've seen that they have some similarities to scattering amplitudes. For example, they're proportional to the momentum conservation delta function. But of course, as they stand, they cannot be really thought of as being scattering amplitudes because they depend on these points z1, etc., zn, that are just points on the worldsheet, and they have no target space interpretation, right? Because I hope it's clear that we're talking about scattering in target space, right? So here we have the string propagating in some higher dimensional space, and the scattering, it takes place in that higher dimensional space, right? So So that's the main point about these models that we're studying, that there is this funny way of describing target space dynamics using two-dimensional field theory, yes? So if you want to think about it in terms of quantum field theory, then what we did in the first part of the course is that we discussed the spectrum of free particles in some higher dimensional, 26-dimensional space, right? These particles, the free particles, are completely characterized by their mass and their Lorentz representation, right? Which means their spin. So that's all we derived from there. We derived the spectrum of masses and spins. So now we're talking about that means that in these higher dimensions, in 26 dimensions, you can write some Lagrangian of free particles, infinitely many free particles. Now we kind of introduce some vertices for those free particles. So those free particles interact through some vertices, as in any quantum field theory. But this is all encoded by these correlation functions in a two-dimensional field theory, right? In the worldsheet field theory of the worldsheet field theory of the string. But the scattering takes place in target space, where the string is propagating. That's the point. That's the unusual kind of way, or something quite unique that happens. So from this perspective, these points z1, zn, they have no meaning. These are just some points on the worldsheet, and moreover, they are not invariant under reparameterizations, right? We can map z to z prime, so these points will be at different positions after such a mapping. So we want to get rid of those points, and well, what's the simplest way of to get rid of those points is to integrate over these points. The idea is, let us now integrate over these points. So these are called integrated vertex operators. These are so we want to compute a correlator of such integrated vertex operators instead. This will be, of course, now independent of the points, so it might have a better, more invariant meaning. And well, roughly speaking, that's our amplitude. This will be our scattering amplitude. So we have here the G string somewhere, -2 plus n. which is the number of vertices that you have for n ends. So this is, everything is here on a sphere, CP1. So sigma equals CP1. But in principle, the whole amplitude is a sum actually it's a sum, yes, over genera from 0 to infinity. Here you have plus 2g. And then you compute on genus G surface. But we are only studying the G equals 0 contribution. So your sigma G is a sphere. And this corresponds to three amplitudes. So you have, for example, 4-point amplitude is like this, yes, in field theory. So if you have more particles, you add more legs. Each leg will add an extra power of the coupling, and so on. So yeah, let's compute this integral. So here we will only study the G equals 0 case. So this is just the integral. Ki with kj times the delta function so that's just the expression we had before, but integrated over all these. And so some kind of home problem is problem or homework is prove that it is SL2C invariant. So SL2C invariant means we have an action of SL2C or simultaneously on all of the points. Well, you can just say that. Okay, let's just like that. So you do a change of variables everywhere here, and you prove that this is invariant. So what is SL2C here? Well, SL2C is the conformal group of the sphere. Yeah, so this is conformal group of CP1. So this means these are transformations that are well defined on a sphere. This kind of map maps a sphere to itself, while rescaling the metric by some factor, right? Just because the metric is dz bar, so actually any reparameterization, holomorphic reparameterization will rescale it by some factor. But the important thing is that this is also a one-to-one map of a sphere to itself. Not every conformal map will map a sphere to itself. So that's a conformal group of a CP1, and because everything was conformally invariant to start with, so it's kind of natural that this is invariant under the conformal group of the sphere, since we're on a sphere. But what's wrong with this integral? So it's a nice integral. I mean, it's a SL2C invariant. Should we calculate it? Well, the thing that's wrong about it is that it's divergent, right? I mean, it's kind of that doesn't exist, if you like. So it's a divergent ring. And why is it divergent? Well, it's precisely divergent because it's a cell-to-C invariant. It's a non-compact group, right? And so you're integrating something invariant. So the kind of the fiber is non-compact and it has infinite infinite volume. So so this is a what I mean is that you should recall that. So now we're exactly in the finite dimensional situation that we talked about earlier. Remember that we have this group orbits, and then it's intersecting some section, but the orbit is the group G, and in this case it's SL2C. Okay, so what we expect is that this integral can be written as an integral over this section times the volume of the fiber, which is the volume of SL2C, which is infinite in any reasonable metric. So so the idea is that instead of calculating this integral, let's just calculate the integral over the section. So we kind of divide by the volume of the fiber. If you well, SL2C is the remaining part of the diffeomorphisms, right? So we had diffeomorphisms, then we fix conformal gauge, we come to conformal transformations, and these are the conformal transformations of the sphere. So we actually should quotient by this residual symmetry. So quotienting by residual symmetry means, well, you could say dividing by volume of gauge group. Of course, when you say dividing by volume of gauge group, that only makes sense if your gauge group is like compact, finite dimensional, and so on. But here it's non-compact. But so we just define basically this integral as an integral over the section. But using that same Fadeev-Popov formula that we had before. So first we applied that Fadeev-Popov formula to some like crazy infinite dimensional integral over some group of diffeomorphisms and so on and so forth. But now we are really in a nice finite dimensional situation, right? So I remind you the formula. So Fadeev-Popov formula. So there was some integral of an invariant function with some natural measure on a quotient over the section. That's kind of what we want to compute. And then this is integral to the equal to the integral over our manifold M. This is our manifold M. There was a delta function, nabla Vg times F. And, well, as you remember, we discussed that actually this guy, nabla Vg, is a, so G of x is the section, G of x equals 0. So that's a gauge fixing constraint, right? G of x. But we discussed that this nabla Vg is actually the Fadeev-Popov determinant. And I mentioned that it's determinant because it becomes a determinant in higher dimensional setting, right? In one dimensional setting, it's just some function. So here, precisely, we have a three-dimensional group. So we have to impose three gauge fixing constraints. And we will have vector fields V1, V2, V3, and gauge conditions G1, G2, G3. And this will be a matrix of derivatives. Okay? So the gauge fixing constraints will be, well, as you also know from conformal field theory, when you have an action of SL2C on a sphere, the simplest or the most natural gauge choice is to fix 3 points. 3 points, right? So we will say that G1 is Z1 minus Z1 0, G2 is Z2 minus Z2 0, what does it mean, Z1, Z2, Z3? This means that actually we have some points on a sphere, so that means we actually have a product of several spheres, right? That's another way of viewing that. So we can set M is CP1 cross CP1 cross CP1. or actually we have more points, we have n points. So we can think of it as CP1 cross CP1 n times, but actually we're only interested in the first 3 points. So let's just, fixing 3 points is enough. 3 points fixes completely your SL2C invariance, yeah? I hope you know that, or else it's a like homework problem. It's easy to bring any 3 points to any other 3 points, non-coincident ones, by using SL2C. So that completely fixes the SL2C gauge symmetry. We have this M, we have 3 gauge fixing conditions. So Z1, Z2, Z3 are coordinates on each sphere, I mean in homogeneous coordinates. Right, and we set them to arbitrary values, well, not non-coincident, of course. And what are V1, V2, V3? These are the vector fields of SL2C on a sphere. More exactly, we have here product of 3 spheres. So we have is G on M, diagonal action. Diagonal action means it acts on all points simultaneously, just like here. So we should write out those vector fields. Well, so the vector fields of SL2C are just d over dz1 plus d over dz2 plus d over dz3. The second one is z1 d over dz1 plus z2 d over dz2 plus z3 d over dz3. Z1 squared d over dz1 plus z2 squared d over dz2 plus z3 squared d over dz3. Right? You know that these are 3 vector fields generating SL2 action. You can compute them. You see that they form the algebra of SL2. For example, commuting this with this gives you this, and so on and so forth. Well, you can derive this just by expanding this transformation in an infinitesimal form, right? Vector fields are just infinitesimal transformations, right? So these are the standard SL2 vector fields, and now I just replicate them 3 times, because they act simultaneously on 3 coordinates. You can think of these as 3 points on one sphere, or equivalently as a point on a product of 3 spheres, right? So I write it as a product of 3 spheres. Okay, and now what do we need to do? Well, we need to find this matrix, this matrix of derivatives. So you just need to act by this vector field on these functions here. That's to find the Faddeev-Popov determinant. Because then we will just have a delta function of these guys. This means just 3 integrations will be done automatically by setting the points to these prescribed values, right? And we'll have our function that we're integrating, this zi minus zj. And the only non-trivial thing is this determinant, which we have to remember. Otherwise, everything goes wrong. So now we form the matrix nabla vi gj. And what is this matrix? Well, this is just 1, 1, 1, z1, z2, z3, z1 squared, z2 squared, z3 squared. Right? I just act by these vector fields on these equations. And the determinant, this thing is replaced with the Faddeev-Popov determinant. So that's precisely the determinant of such matrix. Okay? I mean, we didn't derive it, but it's derived in the same way as we derived this one-dimensional case. So determinant of this matrix, nabla vi gj, is what is minus z1 minus z2, z1 minus z3, z2 minus z3. Right? More exactly, this is, in general, this is called a van der Monde determinant, right? one-Riemann determinant is a determinant of matrix of powers like this. So it's always of that form. And well, you also have the complex conjugate conditions. So you have a SL2 acting on Z's and on Z bars equivalently, right? So you also have that thing will enter. There will be a complex conjugate equation expression multiplying this. So as a result, in this way we drop the volume of the gauge, drop out the volume of the gauge group, and we write just the integral over this section. So section is just means we are restricting to this gauge fixed submanifold, right? This I hope this is clear. This is sits inside CP1 cross CP1 cross CP1. So morally speaking, the amplitude is just the correlation function of integrated vertex operators. But that in itself is infinite, diverges. So we have to actually say that instead of integrating over the whole space, we integrate over the quotient. And integrating over the quotient is tantamount to integrating over the section that represents that quotient. So endpoint amplitude is defined as follows. So an plus 3. Yeah, this is endpoint tachyon amplitude. Like I said, if you want other particles, you have to insert other these polynomials corresponding to vertex operators. So this is G string to the power 1 plus n, modulus Z1 minus Z2 squared, times modulus Z1 minus Z3 squared, times modulus Z2 minus Z3 squared, times the integral over the remaining points. 3 plus k from 1 to n. To n plus 3. And here we have zp minus zq to the power alpha prime kp kq times the delta function of sum of all momenta j plus 1 to n plus 3. Right, so well, the delta function we had before, well, the integral is, now we fixed 3 points, so there were some delta functions, z1 minus z1 0, z2 minus z2 0, right? So we integrate over z1, z2, z3. So actually, I mean, I should, here I just relabel z I0 to zi, where I1 to 3. Right? I mean, when I integrate over z1, z2, z3, z1 gets equal to z1 0, right? z2 is equal to z2 0, and so on. But not to have kind of uniform notation, I just again relabel them to z1, z2, z3. Okay, I hope it's clear. Otherwise, I have to put zeros somewhere, everywhere here, and somewhere here. So I don't want to do that. But we're z1, z2, z3 are fixed, and we're integrating over z4, z5, z6, and so on, whatever we have. And now the nice thing, by virtue of this Faddeev-Popov thing. So this is the Faddeev-Popov determinant. Okay, so this is in this. That this thing is still SL2C invariant. So it's, if you like, again, it's homework. It's similar proof that as for the original divergent integral. So prove that this is and that's important, right? Because that means, for example, that it doesn't really depend on Z1, Z2, Z3. So again, you could move those points around using SL2C. I mean, these are z1, 0, z2, 0, z3, 0, right? But actually, the value of the integral doesn't depend on the values of those points. So, I mean, on where these points are, so you can move them around.
But the integral itself is not SL to C invariant.
Yeah, the integral is not, yeah. Sure, it will cancel against this prefactor. That's why this prefactor is important. But the amplitude is invariant, which is important. So we're kind of then proving that we did nothing bad by picking the 3 points. That it still makes sense, right? So we wanted to get rid of dependence on the points by integrating over those points. But naively, it doesn't work because it will give you infinity. So, but if we fix 3 points, that's fine because it will still be independent of these points, despite appearances. So these enter here, but somehow altogether they cancel. And just some calculation, you do some calculation. So for example, let us see how this works in the 3-point amplitude. 3-point amplitude. Yeah, this is, by the way, 3 plus n point amplitude, right? So 3-point amplitude means we set n to 0. So so we don't have any integrations here in the 3-point amplitude. Just the points are fixed and that's it. So let's A3 is just G string, what we call G string. Then we have this Jacobian, Z1 minus Z2 squared. Times the product. The product is still here. P smaller than Q. So this is ZP minus ZQ alpha prime KP KQ times delta function of K1 plus K2 plus K3. Okay, so now let's use our constraints on the momenta to simplify this expression. So first of all, we have K1 plus K2 plus K3 is 0. Right, so I'll write here. So K1 plus K2 plus K3 is 0. And moreover, each K squared is 4 over alpha prime. Right, the mass shell condition. So let's see what these scalar products are equal to. So for example, let's compute K1 with K2. This is 1/2 K1 plus K2 squared minus K1 squared minus K2 squared. Right, just identity. But then K1 plus K2 is minus K3, so this is K3 squared. So they're all equal to each other, so this cancels against this. And what we get is, this is minus 2 over alpha prime, right? So and same works for any other K1, K3, K2, K3. So all these exponents here are minus 2. And as a result, this cancels against these guys here. Right? So I'm saying that this cancels against this. So the final answer for this amplitude is that this is just G string times delta and this is, well, the amplitude, 3-level amplitude for just a kind of cubic field theory where you have cubic interaction, right, with coupling G string. So that means At least this is consistent with such interpretation, where these are tachyonic legs. So here is the 3-point, and well, our ultimate goal is the 4-point amplitude, so that will be somewhat less trivial. So we just the same formula, but we will now substitute n equal to 1, which means a 4-point amplitude. So 4-point amplitude. So that means n equal to 1. So A4 is G string squared, delta of K1 plus K2 plus K3 plus K4. So, I mean, sum of all momenta. And then you have still the same Jacobian. And d to z, so here z is z4, d to z, and now we have a product of various factors, so z1 minus z2 to the alpha prime k1 k2, z1 minus z3 alpha prime k1 k3, z1 minus z alpha prime k1 k4. So this is all multiplied. Z2 minus z3 alpha prime k2 k3. K2 k4, z3 minus z alpha prime k3 k4. Okay, these are the various factors. So there are 4 points, so 6 of those factors. Of course, not all of them depend on z. So now we can place the points where we like, right? z1, z2, z3 can be sent to any positions that we like. So let's simplify by sending z1 to 0, z3 to 1, and z2 to infinity. So, okay, so z1 is 0, okay. Z3 is 1. So, for example, this is just 1. This is 1. This is 1. So this is actually just 1. So this is also 1. And this is 1. Okay. But now we want to send z2 to infinity. So we have some So we have modulus z2 to the power 4 plus, so there is z2 here, z2 here, and z2 here. So this gives alpha prime k1 plus k3 plus k4 with k2. right? And this is minus k2. So this is modulus z2 4 minus alpha prime k2 squared. And by the Tachyon-Matschaal condition, that's 0, right? The exponent 0, so this is just 1. Well, I mean, we sent z2 to infinity, so we proved everything is SL to C invariant, so that should be the same as sending z2 to some finite point. So the limit should not be singular. So that's what we've proven. And we get rid of this guy and this guy, and this guy, and also this guy and this guy. So, so what remains is just these two factors here. So we get that A4 delta sum of momenta then you have the integral d to z modulus z alpha prime k1 k4 k3 k4. So that's the remaining integral that needs to be evaluated. This integral is convergent for some values of these Mandelstam variables. So in particular, where are the potential singularities of the integral?
0 and 1.
What?
0 and 1.
And where else?
Infinity.
Yeah, at infinity. So 0, 1, and infinity, right? But so you have some conditions. So for example, at 0, what is the condition for convergence of this integral? So z equals 0. Hmm? Well, I mean, clearly this power should not be too negative, right? So it should be greater than something, right? Greater than 0? Well, that's sufficient, but that's not necessary, right?
-1.
That's still sufficient, but not necessary. Yes, -2. -2 is a better guess. -2. No, I mean, yeah, okay, good. But why do you go on in just, unit steps? You could try half integer. I mean, no, I mean, it's like RdR over R squared, right? If the exponent is -2, it's logarithmically divergent, right? Otherwise, it's convergent. I mean, so anyway, so there's the same thing here. And then at z equals infinity, you need that the sum of these guys is what? Yes.
-2.
Yeah, less than -2, right? So same logic applies, right? So I mean, the sum of these guys should be greater than -4, but smaller than -2, right? That's okay. There's some window. So I mean, the way we treat these integrals are treated, you compute them in the domain where they're convergent, and then you analytically continue to elsewhere. So this is basically, this integral can be computed explicitly by means of the trick that, the standard identity that using the gamma function, gamma of alpha rho dt t to the alpha minus 1 to the minus t modulo z squared, standard identity. Then you do this for each factor here. Then z squared is in the exponent. I mean, quadratic form in z is in the exponent. You can integrate over z. Okay. And then you will have a remaining integral over two of the t variables. Maybe actually t is not great notation. Maybe let's call it tau. And there's some more transformation of this integral, but eventually you can calculate it. And we have our amplitude should be a function of how many variables. By 3 variables. I mean, you can just deduce it by looking at the integral, right? How many variables does it depend on? 2 variables, right? I mean, it's 2 to 2 scattering, right? So 2 to 2 scattering depends on 2 Mandelstam invariants, S and T. Usually people say S and T. You can use other variables, but you can take any independent scalar products of the 4 vectors, right? So for example, you could use these as the 2 variables that it depends on. And these guys are related to the usual Mandelstam variables. And ultimately, so for example, S is what? So, you remember there are these 4 momenta, 4 incoming momenta, K1, K4, K2, K3. So, for example, S is K1 plus K2 squared, which by conservation of momentum is the same as K3 plus K4 squared, which is K3 squared plus K4 squared, which is 4 over alpha prime times 2 plus twice K3 with K4. Right, that's an example. I mean, this is K3 squared and K4 squared are each equal to 4 over alpha prime. And then, so you, for example, you deduce that K3, K4 is minus 4 over alpha prime plus 1/2 S, something like that. So you can, then the t variable is K1 plus K3 squared. And use K1 plus K4 squared. There are plus signs because all momenta are incoming or outgoing, alternatively. Right? Sometimes you draw these momenta as outgoing, then you have a difference. So the end point is that this integral is expressed explicitly in terms of some, can be computed explicitly. This integral can be computed explicitly in terms of these S and T and U variables. So S plus T plus U is 4m squared. So this is 4 times 4 over alpha prime. This is 16 over alpha prime. Okay. And the amplitude is G string squared delta of sum of all momenta. And then it has this gamma of 1/4 alpha prime s minus 1, gamma of u minus 1 over the sums of these guys to from u. So this is just the value of this integral if you calculate it and express st, and well, u is just used here for symmetric, to put it in symmetric form. U is a function of s and t, or mean zero. So this is this is what is called the Virasoro Shapiro amplitude. For the scattering of two to two scattering of tachyons in closed string theory. Then you can analyze it the same way as we did for Vincent amplitude. You can look at poles of this amplitude, and you will recover the spectrum that we discussed. There will be these rigid trajectories coming from poles of the gamma functions. So basically that's almost it. I just want to comment on Vincent amplitude. We won't derive it here, but it's the same kind of calculation for open strings. So in case of open strings, comment on open string amplitudes. So in case of open strings, you have same, your original free string was an infinite strip, right? There are some boundaries. Now you replace it by with some Riemann surface with boundaries like this, and each guy like this is an infinite strip. And by the exponential map, it can be modeled on a half plane, right? So where your origin is your infinity at each end goes to the point on the boundary. And you consider vertex operators on a half space placed at points on the boundary. So you compute a similar 4-point amplitude where your vk1 of x1, etc., vkn of xn, x4, vk4 of x4, and you integrate it over all points, dx1, dx4, over the real line. And you see that again it will be divergent. Here you have the relevant group as SL2R. This is the group of transformations preserving the upper half plane. And again, you can pick 3 points, say 0, 1, and infinity. And the 4th point will still be running anywhere on the real axis. So you will have, ultimately everything will be reduced to a single integral over the real axis of some similar product, like x to some power and modulus 1 minus x to some power. And you take that integral and you get the Vincent amplitude, which was had a little fewer number of gamma functions. But roughly it's the same logic. And that's it. So yeah, this way we arrive back at the amplitudes that we started with. So so the idea that we start with some amplitude that has these poles that model the fact that there are infinitely many particles with ever-increasing masses and ever-increasing spins. Moreover, the spins and masses are related by the Regge trajectory, lie on the Regge trajectory. Then, as I told you, it was realized that actually this free string model, upon quantization, kind of nicely describes this precise spectrum. And then, well, the statement is that if you compute the correlation function of vertex operators of corresponding to, or maybe I should say there's one more step. So to each such state, you can associate a vertex operator, and then you can compute correlation functions of these vertex operators. So also, if you go into it more abstractly, there is this BRST technology with BC ghosts, right? You have a BRST charge, and these vertex operators represent the cohomology of the BRST charge acting on operators. So these are also the most general BRST invariant operators. So you compute the correlation function of such BRST invariant operators or just integrated vertex operators, and that gives you some quantity that has the physical properties of a scattering amplitude. And in principle, I mean, if you do it on higher genus Riemann surfaces, you will get loop corrections to your scattering amplitude. In principle, the complete field theoretic counterpart of this is not known, so it's not really known what kind of general field theory corresponds to this, but qualitatively, you can think of it as like I told before, some kind of, say, gravity interacting with higher spin fields. In the case of closed string, or in the case of open string, you also have some gauge field, which is the spin 1 field, right? Also with some higher spin fields. So it's a theory of infinitely many fields with some, in principle, unknown interactions, but whose scattering amplitudes you can compute via this formalism. And yeah, they've been proven to be convergent, so in contrast to general amplitudes of gravity. I mean, just pure gravity, let's say. So that's it. And of course, there are many ramifications of this string theoretic setup. So for example, there are superstrings, which is the most famous thing, right? Which live in 10-dimensional space, but they have on top of the X fields, you then have some additional fermions on the world sheet. And then the formalism is a bit more technically complicated. Then you have, because it's still 10-dimensional, you should consider some compactification. So then there's a whole big story about compactifications, how to choose the compactification, so to preserve various symmetries and so on, like supersymmetry or something like that. But they are in principle much less is known, because even the free spectrum is a very complicated problem. If your target space is not flat space, but some curved manifold, you don't know even the spectrum of free particles, let's say free strings, and let alone like vertex operators and so on. That's a complicated thing. So I mean, yeah, maybe one of the situations where more progress has been done is this ADS5 cross S5 case, which has a lot of symmetry, but still is very complicated, much more complicated than flat space. And well, so I guess that's it. So thank you for attending the lectures.